Hi everyone, my name is Neil Page and my research is on ship-based measurements of atmospheric mercury and bromine oxide in the boundary layer of the Southern Ocean. Okay, so you're probably familiar with mercury. It is the only metallic element that is liquid at ambient temperatures and pressure, and it has traditionally been used in thermometers. However, mercury is extremely volatile, and so it readily evaporates the atmosphere. Once in the atmosphere, it is distributed globally and eventually deposited to remote environments such as the Southern Ocean. In the ocean, mercury can be converted by bacteria into methylmercury. Methylmercury behaves like an amino acid, and so is readily absorbed by living organisms. Once in organisms, it can biomagnify up the food chain and work its way into fish, whales, and sharks. Human exposure occurs when people eat fish, and this can lead to a range of health impacts, such as birth defects and impaired cognitive functioning. Now, I'm focusing on how mercury behaves in the atmosphere, and to assist with this, I've used the global mercury model called GeoScan. Now, GeoScan has been extensively validated against the Northern Hemisphere and a few Southern Hemispheric sites. What we find is that the performance against Southern Hemispheric sites isn't so good. The model tends to have bias and just generally not perform so well, while it has never been compared to observations from above the Southern Ocean before. So, another thing is that polar regions in GeoScan are largely based on what is observed in the Arctic. So, if we go to the Antarctic, again, we see a degree of bias. Because the Antarctic and Arctic regions are quite different, but the model assumes that they're the same. Now, this first graph here shows how GeoScan simulates the distribution of atmospheric mercury above the Southern Ocean. Now, there is a line down here, and that's the observed concentration of mercury from a ship-based campaign, X2. And what we can see is that the model tends to underestimate the mercury concentrations, and I believe this is partly due to the distribution of atmospheric oxidants within the model. Now, the mechanism for the oxidation of atmospheric mercury is shown up here. It is thought that the dominant oxidant of atmospheric mercury is bromine. So, the next thing I wanted to do was assess how GeoScan simulates the distribution of bromine in the model. And we can see that it gets some things reasonably accurate. I mean, it shows high concentrations of bromine in the coastal regions of Antarctica than above the open ocean. And that makes sense because the Antarctic sea ice is a source of bromine in the atmosphere. However, it also shows that it's quite high concentrations of bromine above the interior of the continent. Now, this contrasts with previous studies that have found that atmospheric bromine is fairly low above the continent. So this hints at another layer of uncertainty within the model. If we go to this graph up here, what we have is the observations of BRO in the X2 ship campaign. And what we can see is that the highest concentrations of BRO tend to occur in the surface layer above the sea ice. Now, overall, there are a number of uncertainties remaining regarding atmospheric mercury and its oxidants above the Southern Ocean. To help reduce this uncertainty, further research will target other oxidants of atmospheric mercury, such as iodine oxide, chlorine, and NO2. I will look at the relationship between these oxidants with meteorological parameters and sea ice cover. And I will assess the role of catalytic winds coming down off the Antarctic plateau in transporting both oxidants and mercury to the Southern Ocean. Thank you for your time.